So we started Kirchhoff's rules in the last lecture, and there are two Kirchhoff's rules. One is called Junction Rule and the other one is Loop Rule. So we'll apply those two rules to solve this problem. This question is from your worksheet 9. In this problem you are asked to find currents I1 and I2 and the EMF of the battery. So let's see. So this thing is battery. Okay, so we need to find the EMF of that battery, which is denoted by V, and I1 and I2. So whenever we solve this kind of problem, we need to use both junction rule as well as loop rule. If you just use the loop rule, it won't give you anything in most of the problems. So it's always better to use both junction rule and loop rule. So to use junction rule, consider a junction where all the currents are meeting. So we have two junctions here. One is this down junction where the current in this wire, the current in this wire, and the current in this wire are meeting, and there is this junction where this current, and the current in this wire, they all meet. So consider this junction. Let's call that J. We don't know the direction of the current here. We know there is an ammeter down here, and the function of ammeter is to measure the current. It's not an active circuit component. The only thing it does is measure the current. It measures the current of 3.0 amperes here, but we don't know the direction. But that's not a problem. Okay. So in the last solution, we got the answer of current to be something in the negative value. Okay. So whenever you see a negative value of current, that means the current you chose initially is just the opposite of what is the right direction. Okay. You can choose any direction you like. You can consider that the current is going this way, or current is going down this way. Doesn't matter. If you get your answer in positive quantity, that means the chosen direction is correct. If your current comes out to be positive, it's correct. If it comes out to be negative, that means the direction you chose is just opposite to what you chose. Okay, so we'll just opposite to what is the correct one. We'll see the example of that in the next problem. But for this problem, it is obvious from this junction. So if there is some current going in to that junction, and this current is also going into the junction, there must be something coming out of that junction. It cannot just go all in and nothing is coming out. So we know just by looking at the currents here. So it must be coming out of the junction. Okay. It's not possible that all the current go in the junction and then just disappear. If something is going in, something must also come out. Okay, so that's the direction of current. So the first step to use loop rule, or junction rule, is total current in is equal to total current out. That's the junction rule. So total current in is I1 plus I2. That's the total current in. Total current out is this one. Okay, 3 amperes. So this 3 amperes is all throughout this wire. This I1 is all throughout this wire on the left. This I2 is all throughout this right side of the wire. So that's 3 amperes. Okay, so we use the junction rule. Now let's use loop rule. So you can use loop rule in 3 loops. So we have this loop, okay, this loop, we have this loop, or this whole loop, okay, neglecting this middle part, we can consider this bigger loop. So whichever you like, you can consider those loops, okay. So let's consider this loop, one on the left and one on the right, okay. Now in order to use loop rule, you need to choose some kind of path, okay. You choose either clockwise path or counterclockwise path. Whichever path you want to choose, that's fine. So in this case, let's choose clockwise path. It doesn't need to be clockwise. You can also choose counterclockwise. And in this case, let's choose counterclockwise path, okay. So like that. Just choose one path. So, and then assign the correct signs to all the components. So this battery, this side is positive, longer side is positive, shorter side is negative. This current is entering at this point. Entry point is always positive because current goes from higher potential to lower potential. And exit point is negative. So this exit point is negative. You see this current I2, it's entering from this point and exiting from that point. So entering point is positive, exit point is negative. For this one, current is going down, so this point is positive, that's negative. This battery, longer side is positive, shorter side is negative. So we assign signs to all the components. And now we can use the loop rule. So start with, let's call this loop 1, start with loop 1. So start with any component. Let's say start with the battery. So we are going clockwise, so move clockwise along this path or this wire like this, okay, move clockwise. So when you move clockwise, you are going from negative to positive. Negative means lower potential, positive means higher potential. So when you go from lower potential to higher potential, or negative to positive, the potential difference is positive, okay. And when you go from higher potential to lower potential, your potential difference would be negative, okay. It's like moving uphill or downhill. So if you move uphill, you gain potential energy, okay. So potential energy at the height would be positive. If you go downhill, you lose potential energy, so your potential energy would be negative. Okay, so for this battery, we are going from negative to positive, so that means we are going uphill. So 9 volts. So in loop rule, we just add all the potential differences, okay. So potential difference across the battery is 9 volts, and it's positive. And now we need to look at next component. Next component is this one. So going up along this clockwise direction, the potential difference across this 3 volts, 3 ohms, is potential difference is I times R. So current in this 3 ohm is I1, and resistance is 3 ohms. Now we are going from positive to negative, okay. We are going downhill, okay, higher potential to lower potential. So when we go from higher to lower potential, potential difference is negative, so minus sign. And now next component in this loop is this one, okay. So this one, 2 ohms. So potential difference in this 2 ohm is I times R, I going through that is 3 amperes. Okay, so 3 amperes is the current, and then R is 2 ohms. Now we are going again from positive to negative, higher potential to lower potential. That means sign is negative, and that's all we have in this loop. Okay, so that would be equal to 0. So loop rule tells us that the sum of all the potential differences in a loop is 0. That's the loop rule. Now we can simplify this a little bit. So in the second step, you can just eliminate, or you can just not write the units, okay, to simplify. So units are a little bit messy, so I will not write the units. So 9 minus 3I1, this one is 3 times 2 is 6, is equal to 0. So 9 minus 6 would be 3. Again, take this 3 on the right side, so 3I1. So solving that, I get I1 is equal to 1 amperes. Okay, we got 1 current. Now we can use second loop. So loop 2. So again, choose any component. Let's say start with this battery. In this one we are going counterclockwise. So we are going counterclockwise. So from going from negative to positive would be let's see. So one thing you need to okay, that's fine. So going from negative to positive, it's positive, okay, V, and then the next component is this one going counterclockwise. So the potential difference across this one is I times R. I is I2, and R is 4.5. Okay, and in this case we are going from higher potential to lower potential. That means sign is negative. And the next component going along counterclockwise direction, next component is this one, 2 ohms. So the potential difference across this 2 ohm is I times R. I here is 3 amperes, and R is 2 ohms, and then that's all we have. So ohms for this ammeter, it's not an active component, so we don't need to worry about that. Okay, so this only measures the current. There's no potential drop across that. It just acts as a wire. So this one, we are going from higher potential to lower potential for this one. That means it's negative, and that's equal to 0. Okay, so we have V minus 4.5 I2, take this one to the right side, is equal to 6. Okay, so we have 3 equations. We already found I1. Now we can use this one to find I2. So substitute this I1 in this equation. I1 is 1 ampere plus I2 is equal to 3 amperes. So I2 is 3 minus 1 is 2 amperes. Okay, we found I2 also. And now we can use this third one to find V. So V minus 4.5, I1 is 2 amperes, is equal to 6. 4.5 times 2 is 9, is equal to 6. V is equal to 9 plus 6 is 15 volts. Okay, so V is 15 volts. So we got all three values. So let's look at a little bit more complicated problem where all three i's are unknown. Here one of the i's is known. We only have two unknown i's, but in the next problem we'll have all three i's unknown. Okay, so that would be slightly more complicated than this one. So let's look at this one, number 4. So the first part of the question is asking which of the diagrams represent the same circuit. So basically they all represent the same circuit. They are all same. Okay, they are all same. So how they are all same? So let's see. Let's see if I can show you on some other thing. So there are different ways to write the circuits. They may appear different, but sometimes they are just same circuits. So let's look at that. So this one, this one, and this one. So let's look at these two first. So if I rotate this like this, so you see this junction. This junction is the junction between I1 and I2. So that's the junction, okay, between I1 and I2. Oops. So this is the junction between I1 and I2. That's the junction. And on the side of this I3 we have this 5 ohms. So I3, that's 5 ohms. Okay, and on the side of I1 we have this 2 ohms. That's 2 ohms, and 12 volts. That's 12 volts. Okay, and then on that junction going down we have this 1 ohm. We have 1 ohm. We have 8-volt battery, 8-volt battery, and this 5 volt and 12 volt. I mean this 5 ohm and 12 volt battery are connected at that junction. Okay, so at that junction. So basically they are same circuit. This oriented, shown in a little bit different way. So let's look at the third one. So these two are also same. Okay, so if I rotate this, you see I have 5 ohm here, 5 ohm here, I3 here, I3 here, I1. So basically it's same. 1 ohm, 1 ohm, 8 volts, 8 volts, 2 ohms, 2 ohms. Okay, it's just rotated like that. So but they are same. So all the three circuits are same. So we can just choose one and then find I1, I2 and I3. So let's choose one, whichever you want. Let's say let's choose this one. Okay? Or Let's choose this one. Okay, so let's use loop rule to find I1, I2 and I3. So finding I1, I2 and I3. So first step, either choose the loop, or choose the path, or you choose the signs. Okay, so let's choose the signs first. So this current is going down. Okay, so there is current in this loop, this part of the wire. Throughout this wire, the current is I1, and it's going this way. Okay, so that means current is going this way. So I1 is going that way. It's going down. So this one would be positive entry point. Exit point would be negative. This is negative of the battery. This is positive of the battery. This is negative of the battery. This is positive of the battery. And in this one, the current is going this way. Okay. So it's going this way, I3. So that means this is the entry point of the current, and that's the exit point. Okay. And in this case, the current is going that way. Okay. So the direction is given in this case. I thought like the direction is not given. That's what we need to find. So let's just choose incorrect direction. Okay, deliberately choose incorrect direction. I wanted to show you what happens if you choose the incorrect direction. Okay, so let me choose this way rather than this way. I'm choosing the just opposite direction. So let's say the current is going this way. You can choose any direction you like for the current. If you get the I to be positive, that means your chosen direction is correct. If you get the I to be negative, then it's just opposite to what the correct one is, correct direction is. So if you choose this way for the current, then this is the entry point, that's positive, and that's the exit point, that's negative. Okay, entry point is positive, exit point is negative. So let's make it a little bit less messy. Let's erase that. Okay, the next thing is choose the loop. So let's choose the upper loop and bottom loop, and then choose a path, either counterclockwise or clockwise, whichever you like. So let's choose clockwise path for this upper one and clockwise path for this bottom one. It can be counterclockwise also, whichever path you like. Let's call this loop 1, and that's loop 2, and let's call this junction J. Okay, so start with junction rule. At junction J, there are 3 currents meeting. So total current in is I1. Only the current that is entering the junction is I1. That would be equal to current out. Current out is I2 and I3. Okay, so that's the junction rule. And next is, let's call this equation 1, loop rule for loop 1. So start with any component. Let's start with this one, this resistor. So we are going in clockwise direction, so this way, clockwise direction. That means we are going from negative to positive. So when we go from negative to positive, we are going uphill or at the towards the higher potential. So when we go from negative to positive, our delta V is positive. Okay. So loop rule is sum of all the delta V in this loop is 0. So delta V in this resistor is I times R from Ohm's law. I in this loop is I1. Okay, that's the I1 going through this resistor, and resistance is 2 ohms. That's delta V across that resistor, and it would be positive because it's come from negative to positive. The next component is this battery. Again, we are just going clockwise, so that means we are going from positive to negative. So going clockwise, we get negative for the battery, 12 volts. From higher to lower potential is negative. And in the next part here, just following that clockwise path, for this battery we are going from negative to positive, lower potential to higher potential, so that's positive, 8 volts. And then we have this one. So potential difference across this one is I times R. I is I2. Okay, I2, so that's the current I2, and R is 1 ohm. Now we are going from negative to positive, that means it's positive, and that would be equal to 0. So simplify that, just get rid of the units. So this would be 2I1 minus 12 plus 8 is 6 minus 6. Let's first try this one. So plus I2, and then this one is negative 6, negative 4, sorry, negative 4. I can take it to the right, that becomes 4. Okay, let's call that equation 2. So 2I1 I2, that is equal to 4. Okay, so now for loop 2, start with any component. Let's start with this one. Okay, we are choosing clockwise direction, so we will go from higher potential to lower potential. That means delta V would be negative. Delta V here is I times R. I is I2, okay, and R is 1 ohm. That's delta V. The next one is battery, and we are going from positive to negative. That's negative 8 volts. And the next one is this resistor, and delta V in this resistor is I times R. I is this I3. Okay, this I3 is flowing in this part of the wire. So I3, and R is 5 ohms. And we are going from negative to positive. Okay, so going towards the left, that means from negative to positive, which is positive. So simplify that. Negative I2 plus 5 I3 is equal to 8. That's equation 3. Okay, we got 3 equations. Those 3 equations are I1 is equal to I2 plus I3. Let's call that equation 1. And then 2I1 plus I2 is equal to 4. Let's call that equation 2. And I2 plus 5I3 is 8, and let's call that equation 3. So this one is in terms of I1 and I2, and this one is in terms of I2 and I3. So we want to make them uniform. Okay, we want to write the equation in the same variables. So to do that, let's replace this I1 by this expression. So I1 is I2 plus I3 plus I2, that is equal to 4. So 2I2 plus I3 plus I2, we have 2 also here, that is equal to 4. So 2I2 plus I2 is 3I2 plus 2I3, that is equal to 4. So let's call that equation 4. So we want to now solve 3 and 4, because both are in terms of variable I2 and I3. To solve these two equations, so we want to make one of the terms same, so that we can cancel the term. So to do that, we can cancel I2 and I2. So for that, let's multiply this equation by 3. So that will give us 3I2. 3 times 5 is 15I3, and 3 times 8 is 24. Okay, so let's call that equation 5. Now let's add equation 4 and 5. Okay, so let me rewrite equation 5 here. So negative 3I2 plus 15I3 is equal to 24. Again, that's equation 5. So when we add the two equations, this one and this one will cancel. They are same. 2I3 and 15I3 will add to 17I3, and 4 plus 24 is 28. So that gives I3 is equal to 28 over 17. Okay, and if I do the calculation, I get 1.64 amperes. And then we can use that value in either either 4 or 3. Okay, so let's use this in equation 3. Use I3 equal to 1.64 amperes in equation 3. So minus I2 plus 5 I3 is 1.64 amperes. That is equal to 8. So minus I2 plus 5 times 1.64 amperes is 8.235. Okay, that's 8 amperes. So that is minus I2 is equal to minus 8 minus 8.235 gives me 235 amperes. So that is I2 is 0.235 amperes. Okay, that's I2. Now we still need to find I1, so we can use equation 1. I1 is I2 plus I3, so sum of I2 and I3 is plus 1.64. That gives us 1.87 amperes. Okay, so all the three values are positive. That means the direction that we chose are correct for all three. So in one of the wires, I chose the opposite direction. So it seems like the direction given in the original question is incorrect, or opposite to what it's supposed to be. So if we see the question, so the direction is given this way, but the right direction is opposite to that. When we consider the opposite direction, we got the positive answer. That means the direction we chose is the right one. Okay, so let's look at number 6. When capacitors are in series, we find the combined resistance, find the combined capacitance by using this formula. So we have bunch of capacitors in series, C1, C2, C3, C4. If I want to replace these capacitors by a single capacitor, then I use this formula, 1 over C1 plus 1 over C2 plus 1 over C3 and so on. Okay. If I combine the capacitors in parallel, for example, I have capacitor like this, capacitor like this, capacitor like that. Okay. Let's say this is C1, that's C2, C3, and I want to write one equivalent capacitor for these 3 capacitors. Then that equivalent capacitor, the value of that capacitor or capacitance is given by C1 plus C2 plus C3. Okay. So this is just opposite to what we did in resistors. So when resistors were in series, R1, R2, R3, the combined resistance is given by sum. Okay, R1 plus R2 plus R3, but here is the reciprocal. When the resistors were in parallel, like that, their combined resistance, it is given by this formula, R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So for capacitors in parallel, you add each individual capacitance, whereas for resistors in parallel, you use the reciprocal formula. Okay, so that's what we need to do in this problem. Okay, so let's look at this problem. So let's rewrite the circuit diagram. So we have capacitor C1, capacitor C2, and then capacitor C3, and then we have C4, and then we have a battery down here, so we can just write the battery. So the difference between the capacitor and battery is battery has one long line and one short line, but for capacitor we have the lines of same length. Okay, so that's that. Now we need to first combine C1 and C2. So the combination of C1 and C2, they are in series. We need to use this formula. C equivalent is given by 1 over C1 plus 1 over C2. So 1 over C equivalent is 1 over C1 is 6 microfarad, C2 is also 6 microfarad.
So 6 microfarad is common, 1 plus 1 over C equivalent. So that's 2 over 6 microfarad. So C equivalent would be this and this, you can cancel for 3. So that's 3 microfarad. So now we can replace these two by 3 microfarad. Okay, so you can rewrite the circuit diagram, but this time replace the upper two capacitors by 3 microfarad. So this one is 3 microfarad. This is C3 is 6 microfarad, and this one is 8.5 microfarad. Okay. Now these two are in series, these two are in parallel, 3 and 6. So you can combine these two to get the equivalent resistance, equivalent capacitance. So 3 microfarad plus 6 microfarad will be 9 microfarad. So we can write this as, so replace these two by a single capacitor. Okay. So that's the combination of these two, which is 9 microfarad, and we still have 8.5 microfarad down here, and then we have a battery here. So this is 8.5. Now you combine these two are in series. So for series we need to use this formula, 1 over C equivalent is 1 over C1 plus 1 over C2, or let's just use 1 over 9 microfarad plus 1 over 8.5. Okay, so I will just use the calculator here. Let's see what we get using calculator. So we have 1 divided by 9, that's 0.111 plus let's clear that, 1 divided by 8.5, that's 1176. Now when you add these two plus 0.111, you get that, and then to find C equivalent you take the reciprocal of that. Okay, so reciprocal of that would be 4.37. So our C equivalent would be 4.37 ohms. Okay, so now you can replace these two by a single capacitor, which is 4.37 ohms. Okay, so we just, in this lecture we saw how to get the equivalent capacitance. So the rest we'll do in the next lecture.